So let's continue with the Navier-Stokes equations. What we have seen this morning are, first of all, the statement of the problem that has taken, as you have seen, more than an hour, and then the time integration, which is easy. The idea is that this is not a course on time integration or finite difference methods in time, but just I have just explained the schemes that are needed to integrate in time. So let's make a few remarks about how to obtain the weak form of the problem, which are not very important, but are details that have to be taken into account in the implementation. So first of all, let's consider a more general situation than what we have seen so far. So first, I have not divided by the density, so I have kept the density here. And here, as you see, we have the viscosity, the dynamical viscosity. So apart from dividing by the density, this is the time derivative, the convective term, the pressure gradient, the continuity equation, and here we have another expression of the viscous term different to what we have used this morning. Instead of the Laplacian, here we have two divergence of epsilon of u, where epsilon of u is the so-called strain rate tensor, okay, the strain rate tensor, which is the symmetrical part of the gradient of u, okay. So this is equivalent to the Laplacian because when you take the divergence of this tensor, it is easily seen that the divergence of the gradient is the Laplacian. That 2 cancels with this 2, so that is the Laplacian. And then the divergence of the gradient transpose, the divergence of the gradient transpose can be shown to be the gradient of the divergence. The gradient, it's immediate to see that, the gradient of the divergence. So the divergence of the gradient transposed is the I derivative, the component j of this is the I derivative, instead of the I derivative of uj, is the j derivative of ui, because we have a transpose here, summing for I, okay, keeping j fixed and summing for I. If you assume that derivatives commute, so Schwarz's theorem holds true, this is equal to this, okay, just the Schwarz's theorem. And that is precisely the divergence. So this is dj of the divergence of u. This is the jth component. So altogether, the divergence of the gradient transposed will be the gradient of the divergence, okay. Therefore, if we have that the divergence of u is equal to 0, that should be equal to 0. But it is important sometimes to keep this expression for the reason that we will see in a minute. Okay, so this is equivalent to what we have seen, but somehow more general. First, more general because of the boundary condition that I will mention now, and second, because that allows us to use non-constant viscosities. For example, in the so-called quasi-Newtonian flows, the viscosity is not a constant, but a function of, in fact, of that tensor, in fact, of the invariance of that tensor. Okay. Anyway, so that's an expression that you will often find. So, which are the boundary conditions? So, first we have the initial boundary condition, then a boundary condition of Dirichlet type on a certain part of the boundary. So the velocity given, that could be 0, that in fact is not any problem. And then the important thing is how do Neumann conditions like? How do they look like? They look like this. They look like the normal component of a certain tensor equal to a given vector, okay? And that tensor is the Cauchy stress tensor, as you probably know, and if not, it's defined here. In the case of Newtonian fluids, that Cauchy stress tensor is minus p times the identity, so it's a second order tensor, plus twice the viscosity times this strain rate tensor. This is the so-called Cauchy stress tensor in the case of Newtonian fluids, okay? So why is that the natural boundary condition associated to this form of writing the problem? Because, as we will see now, when we integrate by parts, we will have a contribution from the pressure that is precisely this one, you see? A contribution from the pressure that is this one. The normal component of the stress regarding the pressure terms will be P times N, which is what we will have after integration by parts of this term. And after integration by parts of this viscous term, we will get precisely twice viscosity times the symmetrical gradient of the velocity. Okay, so this is why this is interesting because it's the natural boundary condition associated to the weak form of the problem, and this is the condition that has physical meaning. You know, the point is that that is the condition that has physical meaning, whereas the one that we have used this morning, if you write the natural boundary condition, does not have physical meaning. Let's see, I think I have it written here. Yeah, that's what I meant. That's exactly what I said. So you, to obtain the weak form, you multiply the equation by the test function, you multiply everything by the test function, and then you integrate by parts both the viscous term, you see, in the viscous term, the integration by parts leads to this term. Well, first, let's do 2 steps. The first step is easy. I mean, you move the derivative from the epsilon, you move it to the test function, okay? And then you are left with a boundary term that is this one, the normal component of the strain rate multiplied by the test function. But here is a step that is interesting. What's this step? What is epsilon of u? Epsilon of u is the symmetrical part of the gradient of u. Therefore, it is a symmetric tensor, okay? And that is the gradient of v. However, any tensor can be split into the symmetric and the skew-symmetric part, okay? And what happens with the skew-symmetric part of the gradient of u? When you double contract it with the symmetric part of the gradient of u, which is a symmetric tensor, the result is 0. The double contraction, I don't know if you call it contraction, the summation for all indices of a skew-symmetric tensor with a symmetric tensor is 0. Do you know that? No, I can show you. That's very easy. I mean, if you have a symmetric tensor A, suppose that A is symmetric, A is equal to A transpose, and B is skew-symmetric, is minus B transpose. So if you have a symmetric tensor and a skew-symmetric tensor, and you take the double contraction of these 2 tensors, this is Aij, Bij, okay, by definition, summing for I and summing for J, okay? Now what happens? That summation contains all terms. Now fix A, so it has all terms, fix a given Aj. Now there is no summation. Sometimes you put an underscore to stress that there is no summation. You will have the term Aj, and you will also have the term Ji without summation. So I mean, this is 1, 3, 1, 3, and this is 3, 1, 3, 1, okay, plus all the terms. And what happens with this? Because A is symmetric, this is equal to Aij. And because B is skew-symmetric, this is equal to minus Bij. Okay, so this will cancel with this. Is that clear? So that this is a general rule. The double contraction of a symmetric tensor with a skew-symmetric one is always 0. Therefore, the double contraction of the symmetric tensor epsilon of u with gradient of u will be equal to the double contraction with the symmetrical part. The symmetrical part of the gradient of v is going to be epsilon of v plus the contraction with the skew-symmetrical part, which is going to be 0. Okay, so that you will also see very often in the literature. That's what I mentioned yesterday, I guess. Okay, so this is the integration by parts of the viscous term, and the integration by parts of the pressure gradient, we know it. So we have a contribution from a boundary contribution from the viscous part and a boundary contribution from the pressure term, as I was saying before. Okay, so altogether, this leads us to this expression. After we integrate by parts, we have adding up the pressure term and the viscous term, we have the normal component of the Cauchy stress tensor on the boundary. This is why the so-called natural boundary, I mean natural, not in technical meaning, in technical sense, okay? The natural boundary conditions, you know that in variational problems we have essential boundary conditions and natural boundary conditions. So the natural boundary condition in this case is this one, okay? Okay, so that is it. And therefore, since the boundary condition is that we know the normal stress on the boundary, you know, n sigma equals to h. In the weak form, we just have to replace n sigma by h. Okay, we just have to replace n sigma by h. So this is the weak form of the Navier-Stokes equations, a little more general than what we have seen before because of this term. Okay, so this is the first comment. Very easy, but that has to be explained. Okay. let's introduce some notation. So if that is the L2 inner product, I call this form. Why is it a form? Because it maps vectors to the set of real numbers. So it's a form. It's trilinear if you consider that it has 3 arguments: first argument, second argument, and third argument. Okay, so it's a trilinear form. The point is that the second and the third arguments, or if you want the first and the second, depending on the way you organize them, are the same, are U. Okay, but it's a trilinear form. This trilinear form is what is the convective term. Okay, that's the convective term. That is the viscous term. That is the pressure term. We know that. And the right-hand side, when we have boundary conditions of Neumann type, has also contribution with these boundary conditions. Okay. So the weak statement of the problem can be written as it is indicated here. We have to find U such that this blue equation holds. I think it's easy, but it's a remark that needed to be made, I guess. Okay, as we have said before, the solution has to belong in space to H1. It has to satisfy the Dirichlet condition a priori, and the test function has to be 0 on the part of the boundary where we have prescribed Dirichlet conditions, and has to satisfy the initial conditions. Okay, and we also know that the continuity equation makes sense if the test function is in L2. Okay. So other forms of the viscous and convective term. All this refers to the weak form of the problem. So I have just mentioned that if the divergence of the velocity is 0, this is exactly equal to that, which is what we have used before. And in this case, the viscous term, instead of being that form, is this one. That is what we have used before. Okay. What about the Neumann boundary conditions must be changed? That's a big problem, because when you have this, when you have this form of the viscous term and you integrate by parts, what happens? What you get on the boundary is not the normal component of the symmetrical part of the gradient, but the normal component of the whole gradient. Okay, that's what we have seen, of the whole gradient. And therefore, the natural boundary condition would be with a sort of pseudo Cauchy stress that would be minus p times the identity plus mu times the symmetrical, the gradient of u. Okay, that would be a sort of pseudo Cauchy stress tensor. Why do I say pseudo? Because it is not the physical one. The physical one is this one. Okay, the physical one is this one, and that's why it is sometimes more convenient to write the viscous term in this way. Okay. However, let me make a general comment. What happens in fluid dynamics? In solid mechanics, it is very common to have Neumann boundaries, so boundaries where the stress is prescribed. Okay. In fluid mechanics, it's not very common to have boundaries where the stress is prescribed. Why? Because usually, if we have a confined domain, most of the times what we know is the flow that comes in. So we have Dirichlet boundary conditions. Okay. And if we have, or the flow that is there, if we have an open boundary, usually what happens is that there is flow also outside that boundary. Understand? So in fact, what we are doing is we are cutting the domain artificially. Understand? That's what happens most of the times. I'm not saying always, but most of the times what happens in CFD, in computational fluid dynamics, is that where we have open boundaries or boundaries where the stress is prescribed, maybe to 0, those boundaries are in fact artificial. We have cut the computational domain. And therefore, the stress that we put there, in fact, is always an approximation. Is always something wrong, so to speak. It's never the correct one. Okay. And therefore, sometimes the stress is imposed to be 0, and it doesn't matter whether it is the real stress or that pseudo stress that you would get put in the gradient instead of the symmetrical gradient here. Did you understand the comment, more or less? Okay. So the point is, this is the expression that has the correct Neumann boundary conditions, but it's not that important. It's not that bad if you use the Laplacian. Okay. That's the comment I made. The boundary conditions have to be changed. What about the convective term? What about the convective term? It turns out, since the divergence of the velocity is 0, to that convective term we could add either the divergence of the velocity times u, or 1/2 of the divergence of the velocity times u. We could add any of these because the divergence of u is 0. And they have, both methods have particular properties, both alternatives. One is more or less physical. This one is more or less physical because it is easily checked that u gradient of u plus u divergence of u is equal to the divergence of u cross u. Okay, u cross u. And that expression has physical interest because it conserves momentum. It is a conservative expression. Right? We will not talk about that because we are not going to talk about compressible flow. But that expression has some interest because it conserves momentum. However, the second expression, which consists of adding simply 1/2 of that term, is just only introduced by, let's say, for mathematical reasons, and that was introduced by Temam in the late 70s. Why is this condition interesting? Because in this case, the bilinear form of the trilinear form that defines the convective term, let me call u1, u2, v, is equal to the integral over omega of b dot u1 dot gradient of u2 plus 1/2 of the integral over omega of b dot one half is already there, u1 divergence of u2. Okay, that's a trilinear form of the problem. So what happens if if we take the same argument in the first and the second position? So if in the first and second argument we take the same function. So what we will get is integral over omega of, not in the first and the second, u1. And here in the second and in the third we take the same argument. So we fix u1. And we take v equal to u2 if you want, u2, u2. So we take v equal to u2. What happens? We will have u2 dot u1 dot gradient of u2 plus 1/2 of the integral of u1 of u2 u1 divergent. I don't know if I did that correctly. I don't know if I should have changed the order. I mean, you never know if you have to change the order of u1 or u2 because in the case of the Navier-Stokes equations they are equal. Okay, in the case of the Navier-Stokes equations they are equal. The point is that let me check that. So this is the integral over omega of u2 component j, u1 component I, di, u2 component j. Okay, and this plus the other term, and this is equal. Yes, that is correct. That is correct. Look, this is 1/2 of the other term. Look, what I have done is u1 component j multiplied by the component j of this term, which is u1 component I, derivative I of u2 component j. Right? So that's what we have. And what is the point? I have here u2 component j, and here I have u2 component j. So I can write this as the integral over omega of u1 component I, 1/2 of di of uj, u2 component j squared. u2 component j squared. So that means the Euclidean norm of u2 squared. Okay, the Euclidean norm of u2 squared. And, okay, this is true. I haven't done anything wrong, right? And this is plus the other term, which is 1/2 of the integral over omega of this one. And this one, I never know if as I said, if I should put here 1 and 2, u1, no, I think this is correct. So that should be u2, yeah, okay, that's correct, yes. That this is u1, u2, let me see, this is u2 component I, u1 component I, and this is derivative with respect to j of u2 component j. So I can write that as, should that be 2? Yeah, I'm sorry, that should be 2. that should be 2, yeah. That should be 2 and that should be 1. As I said, you never know which one is which, because at the end, in the application, those are equal, okay? So what's the point? The point is that this is 2, and this is 1. This is 1j, okay? Now, you see that I have here 1/2 of the norm of u2 squared, and here I have the divergence of u1, okay? Now, I can take this derivative and take it out, so this is equal to the integral over omega of di of u1i, well, yes, u1y times the norm of u2 squared with 1/2. But if I put that derivative here outside, I would have what? I would have the term that I already have plus the divergence of u1 multiplied by the norm of u2 squared. So what I have to do is I have to subtract this term. I have to subtract the divergence of u1 times the norm of u2 squared. You see that these two terms are equal to this? Okay? And then what happens between this and this? They are equal, so those cancel. And that's what happens. That now I use Gauss theorem, and on the boundary I have u equal to 0. Or equal to 0, the normal component equal to 0, or in the case if v is not u, cannot be taken as u, is because the boundary condition is not homogeneous. So I have to change to a homogeneous boundary condition. So the point is, what is the good to think about this method? Do you see what happens? That will be 0 always. So the conclusion is that will be 0 always. So this term is always 0. So in the two arguments, this trilinear form is skew-symmetric. I said this morning that the convective term is skew-symmetric. So what's the nice thing about that? What property I haven't used? You see, I haven't used any property. In fact, only the boundary condition. In particular, I haven't used that u1 is divergence free. I haven't used that the divergence of u1 is 0. I haven't used that. You know, I haven't used that the divergence of u1 is 0 because by adding this term, the divergence, the term that involves the divergence of u1 cancels with this one. Okay, so the nice thing is that of this term is that the convective term is skew-symmetric, even if the first argument, the first velocity, is not divergence free. Okay, even if the first argument, if the first velocity is not divergence free, that term is skew-symmetric, and that has interesting, it's not nothing terrible, but interesting mathematical properties. Oh, that is what is said here. That's what I have checked. Okay, I have checked that it's skew-symmetric. By the way, it's equivalent to check that this is skew-symmetric than to check that if the second and the third arguments are equal, then the result is 0. You know that the skew-symmetric form is 0 if and only excuse me, a form is 0 if is skew-symmetric if and only if applied to the same vector the result is 0. Okay, so that's about the weak form, nothing else. So we have seen different ways to see the viscous term, in fact 2 ways, and 3 ways to see the convective term that affect the weak form of the problem. Okay, now we have to linearize the problem because we have a non-linear problem. It's only quadratic, but that's enough. That's enough because that simple quadratic term makes the physics of the Navier-Stokes equations extremely involved. Okay, extremely involved. Only this innocent quadratic term. So now we have to linearize that. Prior to solving anything, we have to linearize that. And for linearizing the equations, we don't need to consider the transient term. In fact, we don't need to consider anything else but the convective term. Okay, we have to consider the convective term. So in order to see how to linearize the problem, we can consider the stationary problem. Time-dependent problems can be dealt with in the same way. And then in that case, we have to assume the following. We have to assume that the convective term is continuous. This is true, but not trivial. This is true, but not trivial. Okay. So what does it say? in fact, this is again Sobolev's embedding theorem. It says that the integral over omega of b dot u1 dot gradient of u2 is smaller or equal the gradient of b in L2, in the L2 norm, times the gradient of u1 in the L2 norm times the gradient of u2 in the L2 norm. That's what it says. And why is this true? What is obvious, what is easy to check, and is that this is smaller or equal the L4 norm of V times the L4 norm of U1. That's what we have seen this morning, okay? Times the gradient of U2 in L2. But it turns out, because of Sobolev's embedding theorem, that this is bounded by this, okay? It is bounded by this. That's what I have mentioned this morning. Therefore, this form C is continuous. So we have this property. Okay, we have this property. The viscous term is continuous. It is also coercive, either because we use the Laplacian form and then we have Poincaré-Friedrichs inequality, or because we have the symmetric gradient, and in that case we have to use Korn's inequality. Okay. The pressure gradient term is continuous, and we have to assume that the Im-sub condition holds, even to prove, as we will see, convergence of the iterative schemes. Okay, so the Im-sub condition appears everywhere; is absolutely necessary. Okay, and then continuity of the right-hand side. Okay, so first result, important result. It turns out that, well, important, but of course, this problem is stationary and it's nonlinear, so it does not need to have a unique solution. This is obvious, right? Why? Because nonlinear problems usually don't have unique solutions. What has to have a unique solution is the evolution problem. The evolution problem has to have a unique solution, but the steady-state problem does not need to have a unique solution. It might have two solutions, but if you look at the time evolution, if you had those two solutions, it's because you have started from different initial conditions. So you start from two different initial conditions and you get two different steady states. And then when you look at the solution in the steady state, you may have two solutions. Okay? That is perfectly possible to have more than one solution, but it's very strange in reality, because for the Navier-Stokes equations, it is very rare that there exist two solutions of the stationary problem. Usually what happens is that when you have two solutions, one is stationary and the other is transient. So to have two stationary solutions is not very common. It's very uncommon. In fact, there is only one well-known case in which you have two stationary solutions of the steady state. Okay, these are the so-called Taylor vortices. Imagine you have two cylinders, and one is rotating in a direction opposite to the other. So they are in relative rotation motion. Okay, that problem has two solutions, and the two solutions are first a trivial one. The cylinder has to be long enough. Okay, there is a trivial solution in which, if you look at the vector fields, they are let's say parallel to the axis, and I mean they are contained in planes perpendicular to the axis of the cylinders. So if you look at the section, they are like that, you know. So this is one solution. This is one solution. So the streamlines are simply circles around the axis. But there is another solution that are the so-called Taylor vortices, in which the streamlines look like a donut, you know. They do like this. Okay, so they are like in a spiral. Okay, so they, as I said, they are like a torus, like a torus. Okay, they live in a torus. So these are the so-called Taylor vortices. This is one of the few cases in which it is known that the stationary Navier-Stokes equations have two steady solutions. But anyway, that's just a comment. Anyway, so it turns out that you can show that the solution is unique, which is very rare, if I was pressing here. It can be shown that the solution is unique if this condition holds. The stationary Navier-Stokes equations have always a unique solution. Well, they have always a solution. That's good. And that solution is unique provided that number is smaller than 1. This is not density here, okay? This is not density. And what is that number? That number, as you see, is the continuity constant of C, the continuity constant of C, that NC, the continuity constant of L, the continuity constant of the right-hand side, and divided by the coercivity constant of A. Let me see. What do you think is the continuity constant of C? Well, the continuity constant of C is just a geometrical quantity, because as you see, here you don't have physical properties, you don't have you don't have data, it's just a physical property, okay? The continuity constant of C is a geometrical property. Okay, that continuity constant depends on the geometry, depends on the domain omega. What is the norm of the right-hand side? What do you think is the norm of the right-hand side? That is going to be proportional to what? What? Even what? F, exactly. Exactly. The norm of L is exactly the norm of the body forces, F, exactly. Okay, and what is the coercivity constant of A? We have seen that. What is the coercivity constant of A? What? Yes, that's true. But in the case of viscous flows, this is exactly equal to viscosity, exactly, to viscosity, excellent. Okay, so this is viscosity, and this is the norm of the body forces. So what does this condition mean? This condition means that either the forces are small or the viscosity is large. Okay, so there exists a unique solution provided body forces are very small or viscosities are large. So we have a small Reynolds number. So this only applies to small Reynolds numbers. Okay, so but this is not difficult to prove, by the way. It is not, and in fact the proof is based on a linearization, although I should not mention that. So let's describe how to linearize the equations, how to linearize these equations. So this is a nonlinear term. And let us denote so we have to design, of course, an iterative scheme, and suppose that we have a guess for the solution U at iteration I minus 1. So I is the iteration counter. We have to start with I equal 1, which means that we have to know U0, the initial guess, a guess, not something, maybe 0, for example, the initial guess. Okay, usually it's 0. So then from U0 we compute U1, from U1 we compute U2, and so on. So suppose that we know the unknown, the guess at iteration I minus 1, and we want to compute the unknown at iteration I, and the same for the pressure. The superscript denotes the iteration counter. Let's call delta U the increment. This is a minus, sorry for this. This is a minus. Okay, delta U is UI minus 1. Okay, and let's take a look at the convective term. The convective term evaluated at the unknown UI can be split in 3 different ways. In fact, in 4 different ways. First, we could evaluate everything at iteration I minus 1, and we would have a term that would be the error that we do, that would be of the order of delta U. That is clear, I guess, because we would have UI plus 1 plus delta U would be UI plus 1 plus minus 1 plus delta U would be UI, and then if we expand, since C is linear in the 2 arguments, we would have terms of order delta U and a term of order delta U squared, which is smaller in principle than delta U. Okay, is that clear? That's an option. Another option is to take that as the unknown that we want to compute and evaluate the first argument in the previous iteration. Again, the remainder is going to be of order delta U, obviously, okay? Because the remainder is precisely C of delta U times UI times V. That would be the remainder, right? Finally, we have another option that is also of order delta U, that is this one. We take in the first argument the solution we want to compute, and in the second argument the solution at the previous iteration, right? So that would be, of course, of order delta U as well. But we could do something more accurate, I would say, which is this. We could compute we could expand that expression and leave all terms except those that are of order delta u squared. And you would have that, okay? That's what you have. So you have ui minus 1 ui, ui minus 1 minus ui minus 1 ui minus 1. How do you get that? Very easily. Let's concentrate only in the first two arguments. So I will write it in general. Imagine we have c of x plus delta x, comma, y plus delta y. Okay? That is equal to c of x, y, plus c of x delta y, plus c of delta x, y, plus terms of order delta x times delta y. Well, I think that is clear, right? For any bilinear form. For any bilinear form, we have this. I have kept this term, this one, and this one. And now you can express C. Imagine delta x is x prime minus x. X prime minus x. So this is, delta x is x prime minus x. And the same for delta y. So this is C of x, y, plus C of x, y prime minus y, plus c of x prime minus x, plus terms of order delta x, delta y. Okay? And then you see, that's what I wanted to show, because we have c of x, y prime, which is this term. This term x minus y cancels with this one. And then we have plus c of x prime y, which is this one, minus c of x y. Okay, so that's exactly what is written here, plus terms of order delta x, delta y. Okay, good. So that's it. These approximations define four possible in principle, linearizations of the convective term that consist precisely in neglecting the remainders. So which is the first sort of methods? Okay, so first we will consider the first three methods. So the first three. Oops, what is that? The first three methods. We will consider the first three methods. So the methods that are obtained here with I minus 1, I minus 1, I minus 1, I minus 1. Okay? So we have this family. So we have to solve, in principle, with this method, we have to solve this equation. So here we evaluate C with u at a certain iteration j and u at a certain iteration j. So first possibility, the first one that is written here, that is in principle of first order. Take everything at minus 1. Okay, that possibility of taking both j equal to k equal to I minus 1, so evaluate the convective term with the previous iteration, can be shown that it yields a solution, but convergence is extremely slow, and only for very low Reynolds number. You can show that that converges only for very low Reynolds number. Therefore, this condition has to be definitely, let's say, abandoned. So you cannot take that directly in the previous iteration and move it to the right-hand side. You cannot do that. Okay, it only converges for very small Reynolds number. If you take j equal I and k I minus 1, there might be no stable solution. As h goes to 0. It turns out that the linear form associated to the problem is not coercive. What happens if this is I and this is I minus 1? So this is I. So how can I close that? Well, close this. So what's the problem if this is I and this is I minus 1? The problem is the following. To obtain stability, I will take the unknown equal to the test function equal to the unknown, right? I will take the test function equal to the unknown. So I will have here I minus 1, ui. And that gives me a term, I minus 1i, that I cannot control, because we know that when the second and the third argument of C are equal, that form is skew-symmetric, and when these two terms are equal, that is 0. But if this is I minus 1, for stability I have to take it equal to ui, and that will not cancel. You understand? Will not be 0. Will not be 0, and I will have to control it. And sometimes it subtracts stability, and that happens in the application. So the conclusion is that that cannot be used, never. So this is forbidden. Okay? You cannot use here u at iteration I, and here u at iteration I minus 1. It doesn't work. Just throw it away. Okay? What does work, and in fact of the three methods is the only one that is good, and is perhaps the best option, is to take that j equal to I minus 1 and that j equal to I. Sorry about that. This is not L. This is I. Okay? So this is I. So that would be I minus 1 I. Okay? Then that's stable because when we take V equal to ui, that is 0, and that doesn't, at least it doesn't hurt. It doesn't spoil stability, and the stability comes from this term that is coercive. Okay? So that's the point. That's the only method that works. It's a sort of, it's a fixed point method, that is this one. That's the problem. That is called Picard's method, which is a fixed point method. So fixed means that we fix the nonlinear terms and solve for the only for one of the arguments. So the problem is linear. So that problem is already linear when we fix that computed from the previous iteration. Okay? So it turns out, what is the property, which is the theorem? It's not difficult to prove, but takes a while as usual. No, I haven't the proof here. The theorem says that for each I, there exists a unique solution to this problem. Okay? Which can be bounded as indicated here. So for each I, that problem has a unique solution that can be bounded as it is written here. That bound is easy to find. Okay, it's not difficult. Okay. Now, for all initial guesses, you take an initial guess. If rho is smaller than 1, you remember that rho was that number that we defined before. So under the same condition under which we can prove uniqueness, it turns out that the method does not only give you a solution for each iteration, but also converges. Of course, that's what we expect. And how is convergence? Convergence is like that. Convergence happens to be in this form. So u minus u at iteration I is smaller or equal rho times u minus u I minus 1 in norm. So that means that if rho is smaller than 1, we decrease the error between the converged solution and the solution at iteration or I at each iteration. You understand? And so if we repeat that, if we proceed inductively, it will happen that u minus u at iteration I will be smaller or equal what? Rho to the power of I u minus u at iteration 0, which will be a number, a given number. Okay, so that depends on the initial guess. So if you call it the error at iteration I, what happens is that the logarithm of the error at iteration I will be equal to a constant, which is the logarithm of this, plus I logarithm of rho. And since rho is smaller than 1, this is smaller than 0. So we have a slope, a negative slope, in terms of the number of iterations. So the method is said to be linear, to have linear convergence. Okay, linear nonlinear convergence. Okay, linear convergence of the nonlinear procedure. Newton-Raphson. Newton-Raphson is the second method. You could obtain that through taking the derivative of that functional, but it's not needed. In the case the functional is quadratic, you can play that game and that's it. But you could also obtain that through by taking the Jacobian of the associated tangent matrix, but that's not important. So that's Newton-Raphson's method. The fourth option is Newton-Raphson's method. So we have here C u at iteration I minus 1, u at iteration I, and also this term, you know. This term alone doesn't work. This term alone doesn't work. But if you add this one and then you put in the right-hand side this one, that does work. Okay, that does work. Under which condition does that work? Under these conditions. First, we have to have rho smaller than 1. If rho is greater than 1, it doesn't work. And then if rho is more than 1 and u minus u0 satisfies this property with sigma smaller than 1, and c this constant, c is a given constant, but sigma has to be smaller than 1, then the solution exists and converges in this way. Okay? First, what does that mean? That u minus u0 has to be smaller than certain quantities. It means that we have a certain condition on the initial guess. The initial guess cannot be arbitrary. We have to be close enough to the final solution. This is the so-called attraction ball, or the radius of the attraction ball of Newton-Raphson's method. Okay, Newton-Raphson's method. So we have to be close enough to the initial condition. And the problem is that that constant grows, so 1 over that constant grows with the Reynolds number. The higher the Reynolds number, the smaller that constant is. So that's a big problem, because we have to have a very good solution to start Newton's calculation. And the second remark is that convergence is said to be quadratic, although this is a misleading name, because what happens is this: u minus u at iteration y is bounded by a constant times sigma times 2 to the power of I. So in nonlinear methods, this is said to be quadratic convergence, but in fact, if you plot the logarithm of the error against the number of iterations, it's not a parabola. Quadratic here doesn't mean a parabola, but means a power law. It's a power law. Here are the plots. You know, first of all, the first comment is that that's the attraction ball of Newton's method. U minus ui has to be close enough, so that has to be small enough. So when you increase the Reynolds number, that difference has to be closer and closer. So when the Reynolds number is very large, you have to have initial guesses very close to the solution, which you don't know, and therefore it's difficult. And that's the plot of the logarithm versus the number of iterations. So it's called quadratic convergence, but in fact this is a potential curve. That goes to 0 extremely fast. When Newton's method works, it's beautiful, because in 2 or 3 iterations you get a very small residual. Okay, now we are done. We have those are preliminaries. What we have seen, so we have this morning we have seen the 4 topics. First is the statement of the problem. That is what has taken most time, because that's an important problem. Then we have seen the time discretization, the time approximation. Then some comments about the weak form, and finally how to linearize the problem. Okay, how to make the linearization. Okay, now let's go. Now we are in a position to perform the finite element approximation already. Okay, so we can use any time integration scheme and any linearization, but let's assume, for the sake of conciseness, that we use the generalized trapezoidal rule. So that means that we evaluate everything at a certain point n plus alpha. Remember that this is the convex combination between n plus 1 and n. Okay. So we evaluate everything at n plus alpha, and we discretize the time derivative using that incremental quotient. Remember that delta un means un plus 1 minus un divided by delta t. And the rest of the terms are evaluated at n plus alpha, except the pressure gradient. I said this morning that it's irrelevant whether it is n plus 1 or whatever, doesn't matter. And the continuity condition, that's full of little mistakes. This should be n plus 1, okay, n plus 1. Okay, and the continuity that is imposed at n plus 1. Okay, good. Now that we have this weak form linearized, you see, by the way, the linearization here is Picard's linearization, okay, the simplest. So we compute that at iteration I, and we compute this at iteration I plus 1, okay. So it's a fixed point or Picard's linearization. Good. So now we can do finite elements. Let's do finite elements. The Galerkin method is trivial. We have to construct a finite element space for the velocity, a finite element space for the pressure, and then replace continuous functions by finite element functions everywhere. So the solution UH belongs to the finite element space, and the test function VH and QH, both test functions belong to the finite element space. As simple as that. Which is the matrix structure of this problem? The matrix structure has the same matrix structure as for the Galerkin method, as for the Stokes problem, with 2 remarks. First, in that term that multiplies the velocity, we have a contribution from the convective term, and therefore that matrix will depend on the velocity unknowns as well. So we have a nonlinearity here. We have a nonlinear term because of this, because of the convective term. And second, we have a contribution from the time derivative, of course. which is the expression of these matrices. Easy. It's given here. The expression of these matrices is, we know the expression of the viscous term when using the, by the way, this is obtained when using the gradient form of, the Laplacian form of the viscous term. We know that. That is the contribution from the pressure gradient and the incompressibility constraint. And now we have a contribution from the convective term and also this term that comes from the time derivative. This mass, which is the product of two functions, is called mass matrix, as you probably know. So the matrix that appears, in this expression, that matrix is called mass matrix. Okay. Good. So very simple. Very simple. What else? Nothing else. Yes, the other comment is that the velocity and pressure interpolation in principle may be different. In fact, we know that in order to satisfy the if-sub condition must be different, okay? Because that's the Galerkin method, nothing special. That's the Galerkin method. Let me make a comment concerning, yes, a comment concerning the time integration. What we have done now is to discretize in time first and then in space. Okay, that's what we have done. First discretizing in time and then in space. There is also the possibility of discretizing first in space and then in time. That's the so-called method of lines. It's just a comment, what comes here. It's a method of lines. So what do we do in this case? Well, in this case, we obtain first the variational form of the problem. This is the variational form. That's the time derivative that now is continuous. It's not discrete. The convective term, viscous part, pressure gradient, and incompressibility constraint. And then we discretize first in time, in space. We discretize first in space. So what we do is we replace U by UH, a finite element solution, and V by VH, okay? And how does this finite element approximation look like? So we approximate U, the velocity UH, which depends on position and time, by the sum for all nodes of the shape function of node A of the velocity shape function, which depends on position, times the nodal values. And of course, if this is a time-dependent function, the nodal values now are time-dependent. Okay, the nodal values are functions of time. Okay, so when we replace this expansion, this one, in the equations, what we get is that system. That system is a system, as you see, of ordinary differential equations for the nodal unknowns, which depend on time. So we have the time derivative of the nodal unknowns with an algebraic constraint. Those are called differential algebraic systems, as you might know. It's DAE, DAEs, okay? Differential algebraic system. So it's a differential system with an algebraic constraint, okay? Anyway, but it's equivalent to discretize first in space and then in time, or using the Galerkin method to discretize first in time and then in space. Now what do we have to do? We have a system of ordinary differential equations with an algebraic constraint that we have to discretize in time. Okay, so we discretize in time now using any of the techniques that we have seen before. Okay, oops, sorry. Any of the techniques that we have seen before, okay? So, there is another possibility that I just want to mention, and this is closely related to the variational multiscale framework because that was very much used in that context for reasons that we will see, which is the space-time finite element approximation. The space-time finite element approximation. What is the idea? The idea is that instead of working in space and then discretizing in time, write down a variational equation in space-time, and approximating also in time using finite elements. Let me make a comment prior to anything. Is it what is the advantage of, let's say, sort of philosophical comment? What is the main advantage of finite elements? The main advantage of finite elements is the flexibility to deal with general geometries. This is something that everybody will say, and that is obvious. If you have to work always with squares, don't use finite elements. If your domain is always going to be a square, finite elements are more expensive than finite differences. That's obvious, okay? So don't use finite elements. What happens in time? The time domain, the space-time domain, is always cylindrical, always. So time, we have a domain like that, and time always goes in that direction. And maybe I mean, it may deform in time, the domain. The domain may be deformed in time, but always the shape will be cylindrical, okay, always. So using finite elements in time, the first remark is that, you know, I think it's nice from the theoretical point of view. From the application point of view, it's really unnecessary. That's the first comment. Why? Because the geometry is always simple. That's the first point. Second point. If you use finite elements in time, you have to use necessarily a discontinuous interpolation in time. Why? Because if you use a continuous interpolation in time, what happens? Imagine this is time, and this is the time step n, node n, let's say. And this is node n plus 1. And this is node n minus 1. So when you test against solutions at time step n, imagine that you are testing with linear functions, for example, linear functions. The function associated to this node looks like that. And when you test against that, the equation will necessarily involve the solution at un plus 1 at un plus minus 1. So when you test with solutions at time step n, you will need also a solution at time step n plus 1. And when you test at n plus 1, you will need the solution at n plus 2, and so on and so forth. So what happens is that all time is coupled. So to compute the solution in the first time step, you need the solution at all times. Everything is coupled. So the conclusion is that the interpolation in time has to be necessarily discontinuous. Discontinuous in time, okay? The solution in time has to be necessarily because otherwise we increase the dimension by 1. First of all, from the physical point of view, it's not very nice, because if you couple everything, you violate the so-called principle of causality, the cost. I mean, you know, the principle of causality states that something that happens now does not depend on what will happen later on. Very simple. So this is violated by this interpolation. So what happens now depends on what will happen a few minutes later. Okay. So the interpolation in time has to be discontinuous. Good. That's the first point. If you want a variational method, because you be careful, because in the literature sometimes you will find people that say that the interpolation is discontinuous in times, but then they weight the equations against functions that are discontinuous in time. So they mixed a little bit the concepts, you know. That's possible. You obtain an approximation, but it's not a variational approximation. Okay, so what we will do then is the following. We consider a partition in time, and then we divide the time in time intervals, as usual, and we consider what are called space-time slaps, okay? So that's the spatial domain omega cross a certain time interval. So that's space-time slap. Which parallel?
Parallel mother is kind of doing time.
But I don't follow you. What do you mean?
I mean, the parallel approach for
parallelism, you mean?
No, parallel.
Parallel?
Yeah.
I don't know what parallel is.
Maybe we can update that.
Okay.
That is scheme of.
A parallel is a scheme by who?
The group, the French group.
Oh, the French group. Okay. But this is different. This is a slightly different approach.
Slightly different approach.
Yes.
They
deal continuously in time, but in fact they solve two problems.
Two problems, yes. Source and affine.
Yeah, but this is a little bit different. Okay, that's not exactly the same. So yes, that's true. There are many alternatives. Many alternatives. Yes. Okay, so. Let's consider, as I was saying, a space-time slap, omega cross a time interval. And also the elements, we can consider a space-time element, which is an element in space cross that time interval. So that's sort of as a prism, okay? That's a prism, the domain in space times the time interval, okay? And now we consider the Navier-Stokes equations integrated over a space-time slap. And the test functions also time-dependent. Okay, so now we don't have the test functions time independent, but time dependent. So what we have is the integral over time and the integral over a space. The integral over a space is also taken into account in the forms C, A, and B. So now we have to integrate also in time. Okay, we have to integrate in time. Now let's play a little bit with this term, with the time that term. Now V is a function of time in that approach. So it's like, you know, a global variational method. But I can integrate only in a certain time interval because I will assume that the test functions are discontinuous across time slabs. Understand? So that's why that allows me to integrate only in a time interval and not in the whole time domain, but only in a certain time interval, because I will assume discontinuous interpolation in time, and therefore I can take the test function, which is time dependent, to be different from 0 in that time interval, but equal to 0 on the rest. That's what allows me to do that. Okay.
H is a 0 outside that time interval.
Yes. Yes, exactly. Okay. And that's possible because the interpolation is discontinuous. I mean, you can see it in different ways, but in particular, what you are saying is maybe the simplest option to see that. We are integrating only in a certain time interval because we can take V to be 0 outside that time interval. Okay? So it's necessarily discontinuous. Okay? Good. So now we do the following. We integrate by parts this term. We also integrate by parts. So that is the derivative of the product. And of course, since V is time dependent, we have to subtract the U derivative of V. And now, the point is that the integral of the derivative is equal to the values on the edges of the interval. So it's the value of the solution at n+1, which is the upper limit of the interval, minus the value of the integrand at n. So the value at n+1 minus the value of the integral at n. And the notation employed here is the following. So we have, that is the time axis, that is the interval in, okay? That is time n+1, and that is time n, okay? And the solution is discontinuous, like this, for example. Solution will be discontinuous, okay? So in the time interval in, I will denote, or we denote, the solution at Tn+1 as U at Tn+1, I have used subscripts, at Tn+1 from below, okay? That is going to be the solution at Tn+1 from below. And that's going to be the solution at Tn+1 from above. And likewise for the solution at time Tn, any function, not only the solution, but any function, okay? But any function. Okay. So now what we do when we have these, so far we haven't prescribed any initial condition. What we do now is we impose that the solution at time Tn from above, so the solution here, you see the red spot, the solution here, time is equal to the solution at time Tn from below. So that means that we replace this value by this one, you see? What are we imposing? We are imposing, from the physical point of view, so to speak, we're imposing as initial condition in that time interval the solution obtained in the previous time interval. You understand? We impose that in a weak sense, weakly, we prescribe weakly the condition that the solution in the time interval in is equal, at the beginning of the time interval in is equal to the solution at the end of the time interval n-1. Is that clear? Yes?
Some sense.
No, but in a weak sense.
Yeah, in weak sense.
Yes, we impose continuity in a weak sense, of course.
Yes.
But of course, it will be very different, as we will see. I mean, it can be readily seen. I don't know if I have it here. Yes, I have it here, for example. So that's the final method. The final fully discrete problem is this one. So we have that term, which is this one that remains. We have those two terms that are rewritten here, and then the rest of the terms. This is the space-time, in that case, Galerkin formulation, using finite elements both in space and in time, but discontinuous in time. So first remark. We have obtained that, you know, from integration by parts of this temporal derivative. And why have we integrated by parts? We have integrated by parts because that makes that term appear, and we can prescribe weakly the continuity from one time slab to the other. That's why we have integrated by parts. That's the first remark. But it would be possible to obtain directly this expression using concepts of discontinuous Galerkin methods. Okay? So I haven't done that, but that can be obtained directly using the classical concepts of discontinuous Galerkin methods, and in that case with full upwind is called, okay, with full upwind. Okay? So that can be obtained also from the concept of discontinuous Galerkin. So we haven't talked about discontinuous Galerkin methods, but that could be done. Okay? Discontinuous Galerkin are very important, so I am spending more, in my courses, I am spending more and more time to explain DG methods because they appear in most time. For example, this is one of the applications in which they are interesting, okay, DG methods, time problems. Okay, that's the first remark. So, first remark, for piecewise constant interpolations in time, if we have a piecewise constant interpolation in time, is that if that instead of being linear is piecewise constant, we recover the backward Euler scheme. Why? Look, imagine the interpolation in time is continuous. What is that? The time derivative of v. What is that within the interval in? 0. Boom, 0. And that we don't have to distinguish between un plus 1 minus and un plus. It's just the same. We can call it u at n plus 1, you know, because the solution here will be the same as the solution here, because it will be a straight line. It will be constant in time, okay? Good. So we have un plus 1 minus un, you see, un plus 1 minus un. We don't have to distinguish between these two, vh, just call it vh, plus the integral over time of all these terms. But if the interpolation is piecewise constant in time, does this depend on time? It's constant in time, so it doesn't depend on time. So we can take all that square bracket out of the integral, and we have the integral of it over the time interval of delta t, and that's what? Equal to what? The time step size. Okay? We take that out because it's constant, and we have the time step size. So at the end we have u at n plus 1 minus un plus delta t times all these equal to the right hand side. And this is precisely backward Euler, isn't it? You just have to divide everything by delta t. Well, in fact, there is then the right hand side, instead of being the force evaluated at n plus 1, would be the mean force in the time interval in. Well, anyway, it's a slight difference in the right hand side. A very bad point, terribly bad point that, in my opinion, makes this method very computationally unaffordable. So imagine, if you want to have a second order scheme, I anticipate that, for interpolations in time of order q, the time accuracy is order q plus 1. So imagine you want to have a second order scheme. So what should q be if you want to have a second order scheme? It should be 1. So if you want a second order scheme, q should be 1. That means that you have to have a linear interpolation in time. If you have a linear interpolation in time, how many degrees of freedom do you have? You have, that is going to be unknown, and that is going to be unknown. So you have twice the number of degrees of freedom of the space approximation. You double the numbers of the degrees of freedom, you see? Whereas in the case of a classical finite difference method, those methods that we have seen this morning, you have the same degrees of freedom as for the spatial approximation. You just un plus 1, un plus 2, and so on. Here you double them. You double them. It's not just increasing a little bit, it's doubling the number of degrees of freedom, okay? So that makes the method very expensive, very expensive. But the method is unconditionally stable and very nice. So the way to avoid that problem of doubling the number of degrees of freedom is solved by using predictor-corrector schemes and so on.
This term c plus a minus b, this is independent of time?
Of course.
Why?
Why? Because independent of time, within the time slab in, okay?
Yes.
Within
B
the
is
time.
constant?
No. What is no, no? U is constant.
Okay,
U is constant. V is constant. So everything is constant in time.
Okay.
So if everything does not depend on time, of course it's different from time step to time step.
Yes, sir. If
But
V
for a
is
given
constant-
time step, it's constant. So you take it out of the integral.
Yes.
Okay. More questions? No more questions? Well, the method is unconditionally stable. Well, let's see. Now, let's obtain a. That was just a remark, okay? That was just a remark about space-time approximation. So you will see very often space-time approximations in the literature, and well, they can be used. Okay, they can be used, and that's it. Now, what we are using the Galerkin method. We have done the space-time the space approximation using the Galerkin method. Let's obtain a stability estimate for the Galerkin method and see what we don't have. Okay, this is very easy. This is very easy. For the moment,
The TG sense what happens, I suppose if you just
what happens in which sense?
this is equivalent to DG formulation, correct? In time.
This is the gene time, yes.
So this comment is unconditionally stable holds for that.
Holds for the all interpolation orders and time step
And also
sizes.
that linear distance possible.
Yeah. For all methods, it's unconditionally stable. Yes, the method is unconditionally stable. It is not difficult to show that it is unconditionally stable. Yeah. So it's not that you have to worry about the size of the time step. You can use time steps as large as you want. So what do you have when you use the Galerkin method? Suppose that the convective term is skew-symmetric. So we use the skew-symmetric form of the convective term. Remember, that is the u gradient of u plus 1/2 of u divergence of u. That's the skew-symmetric form. So if you take the test function equal to the unknown, what happens is that this is 0. This is equal to the viscosity times the gradient of u squared, if you use the Laplacian form. If not, that could be the symmetrical gradient. And then the right-hand side can be bounded, of course, in terms of the h1 norm of the unknown and the h-1 norm of the forcing term. That's the definition of h-1, if you want. So at the end, that's the same as for the Galerkin method, as for the Stokes problem, exactly the same as for the Stokes problem. What we have is this estimate. Do you remember that we said that in the case of the Stokes problem? Why? Because the convective term is 0 when you take the test function equal to the unknown. And what did we say about the Galerkin method applied to the Stokes problem? Why it doesn't work? Because we don't have control on the pressure. You remember? And here, using the Galerkin method, we don't have control on the pressure. But that's even worse, because in this case, we don't have control on the pressure and we don't have control on the convective term. You see? So in the case of the Navier-Stokes equations, we have combined the two problems that we encountered on the one side for the convection diffusion reaction equation and on the other side for the Stokes problem. So we have the problem of lack of control on the convective term and lack of control of the pressure. We have both problems together. Okay? So from these estimates, we see that first, if the viscosity is small, if that is small, then the control on the derivatives will be very weak, and in particular the convective term will be out of control. So if viscosity is small, we have the problem of convection dominated flows, and there is no explicit way to control the pressure. Okay, so pressures have to be controlled by other means. That's what we said for the Stokes problem, and that's what I mentioned exactly for the Stokes problem. The only possible bound to the pressure is that for each pressure, there exists a velocity such that we have this bound. Why? Because pressure only appears in the momentum equation through this term. You remember? That's exactly the same argument that we used yesterday for the Stokes problem. It's the only way where we can extract pressure stability from the inf sub condition. So using the Galerkin method, you have to have inf sub stable approximations. And that's exactly what I said before, so it doesn't, that's the same as for the Stokes problem, nothing new. So that condition is known as inf sub or Lenskaya Babuchka-Brezzi, since Lenskaya proved that in the continuous case. It is a particular case of an abstract stability condition that was used by Babuchka The abstract result, let me remind you that the abstract result is called Babuchka-Banach-Nekas theorem, and in fact the deep result is due to Banach. And it was obtained by Bretzi as a condition under which the Stokes problem is well posed and its finite element approximation has optimal convergence rate. This is exactly what I said yesterday, so nothing new here, okay? Well, and now, if we, let's say, keep aside for a moment the problem of convection-dominated flows of small viscosities, if we only want to deal with the compatibility between pressure and velocity, we have exactly the same situation as for the Stokes problem. So we have a set of elements that can be used and some that cannot be used. So we have two problems. We have to satisfy the Imsub condition, and we have to deal with convection-dominated flows. That's it. What do? We stabilize it. We stabilize it, and again, that section is going to be very fast because I have explained it, well, I have explained it once. We have gone fast through it in the Stokes problem, and then we will go fast through it in the Navier-Stokes case. So we will see the subgrid scale concept once more, very, very rapidly, and how to apply that to the incompressible Navier-Stokes equation. Nothing of what I will say now is new, okay? We consider an abstract problem. I will make a remark, though, later. We consider an abstract problem, stationary for the moment, linear for the moment, stationary and linear for the moment. We that's the bilinear form. We decompose the solution into the finite element solution plus the remainder. We integrate by parts. We have the equation for the subgrid scales. We solve for it, the same thing. We can have different approximations, either the Green's function or whatever. So at the end, we have this term. Everything goes smoothly. Another approximation is the use of residual free bubbles, all exactly the same in slides with the same mistakes. And we may go ahead, and those are residual free bubbles. That's it. And finally, the application to the Navier-Stokes equations. So this is the problem we want to solve. I also explained that in the case of general advection diffusion reaction systems. For completeness, I have included, apart from writing the now we understand this, okay? In the first, when we were talking about general convection diffusion reaction systems, I didn't have an explanation for that. Now we do. So we add this term to the convective term so as to have a skew-symmetric convective term. So these two terms are skew-symmetric, okay? So this is the Coriolis term. If you write the equations in non-inertial frames of reference, and that is the porosity term. And that, we also understand that now, because we have seen the Stokes problem, we also understand the reason why it might be useful to introduce this condition. For example, if you want to have a zero mean pressure, you have to have this term, okay? So we all understand that. So the objective to stabilize this is manifold. So first, we want to use any, in fact not equal, but any velocity pressure interpolation. We want to avoid the need for satisfying the Babuchka-Bretzi condition. We want to be able to deal with highly convective flows. We want to be able to deal with flows dominated by the Coriolis force. Or we want to alleviate localized oscillations due to low permeability. Okay, when permeability is very low, that coefficient sigma is very large, this is the inverse of the permeability, then we may have problems. Okay. So that's what I wrote for the general convection diffusion reaction system. I will not explain that again. So we have to follow the general procedure. At the end, what we have to do is to add the adjoint of operator applied to the test function, multiplying the residual and multiplied by tau. Okay, that's what we have to add. At the end, what we have to do is to add this. So we add this to the Galerkin method, and that's it. If from the convergence analysis it turns out that this is how it has to behave, and that's it. And here is where I wanted to stop, and I will stop with a remark, with an important remark. So what do people do? In fact, I will one of the additional sessions, I mean, once we finish Navier-Stokes, those are the three main blocks that I wanted to explain. So convection diffusion reaction, Stokes, and Navier-Stokes. Okay. Now there are four more topics that will be for the 4 sessions that remain, apart from Tomorrow I will explain a little bit about fractional step methods, but this is only a complement, let's say. And the first topic about which I will talk, so far, I haven't explained any of the things that we do in our group, nothing, okay? Now the 4 additional, or nothing, I mean, as much as possible I have tried to keep the exposition to general, okay? So, what do people usually do when we apply this to a nonlinear problem? So the idea, the argument that people use is that when computing the approximation to the subgrid scales, the convective term is said to be linearized around the finite element solution. What does that mean? It means that the equation for the subscales, remember that is L of u tilde equal to the finite element residual. That is the equation for the subscales, okay? But imagine the problem is non-linear. So in fact, our operator L, in our case, is L that depends on u times u equal to f minus the finite element residual that also depends on u. Okay? Why? Because of the convective term. So that means that the equation is u gradient of u tilde minus viscosity, Laplacian of u tilde, and the gradient of the pressure tilde equals f minus u dot gradient of uh minus nu Laplacian of uh plus gradient of pH. And then the incompressibility condition, okay? So what is the argument that people do? People say, okay, we have a nonlinear term. We have a nonlinear term. That velocity u, in fact, if you accept your original decomposition, is uh plus u tilde. If you accept your original decomposition. However, in 90% of the papers, you will see that, okay, in order to obtain this subgrid scale, we assume that u tilde dot gradient of u tilde is negligible, because in principle the subscale is much smaller than therefore this is replaced by and this is also replaced by here, understanding that u tilde is, as I said, smaller than and here you only have to consider okay? That's what people usually do. So in general, in 90% of the publications in this field, you will see that the equation for the subgrid scale is linearized around the finite element solution, okay? It's linearized around the finite element solution. So here you put, instead of putting u, you put okay? Well, we don't do that. I will explain when finishing the Navier-Stokes equations, we don't do that. That's one point. Second point, what about the time derivative? What about the time derivative? Exactly the same. If you have the time derivative of u, in principle, this is equal to the time derivative of plus the time derivative of u tilde. And people say, okay, this is negligible against this. And therefore, they neglect that. We don't do that, okay? Or not all the times. Sometimes it's easier. We will see the difference between one thing and the other, but this is something that we do in our group, okay? So it's not something general. So the message is, in general, when people try, in general, I'm not saying always, in general, when people try to apply these variational multiscale techniques or subgrid scale techniques to nonlinear problems and time-dependent problems, what they do is they linearize around the finite element solution, and they suppose that the time derivative of the subgrid scale is negligible, okay? That is what people commonly do, 90% of the cases in most situations. And of course, if you have linearized around the finite element solution, the advection velocity that appears here is the finite element velocity. A, in the case of Navier-Stokes, is itself. And as you see, that introduces another important nonlinearity, because now the stabilization parameter depends on the solution, depends on the velocity, which is what you want to compute. And therefore, that introduces additional nonlinearity to the problem, both tau 1 and tau 2. Okay? And now that's it. So perfect. Now we will, tomorrow we will devote maybe half an hour to that topic, which is a little bit outside the stabilization about the problem, but I think is important for completeness. Okay, so I will talk a little bit about fractional step methods, and then we will continue with the topics, the additional topics, so to speak. And the first one will be turbulence. Okay, the 4 topics that I have prepared. Maybe if you are interested, you can ask me if I have, let's say, enough material to talk about something else. But the 4 topics about which I was planning to talk, that could be open, but the 4 sessions, so that's more or less progressing as I was thinking. So there are 4 sessions, and for each of them I had prepared one topic, maybe not exactly session by topic, but altogether 4 sessions, 4 topics. And the 4 topics are turbulence, so that's, using our point of view, I will talk about that tomorrow. Darcy's problem, well, they are listed here. Darcy's problem, waves, and magnetohydrodynamics. So those are the 4 topics I was planning to talk about. You see, one is this one, turbulence. That I will talk about this tomorrow. Then Darcy, I will talk about that tomorrow afternoon, probably, if you are interested. Oh. Darcy, and then Maxwell's problem, magnetohydrodynamics, doesn't open. Magnetodynamics, and finally waves. So they are very different problems, and I think they give an overview of how to use these variational multiscale techniques in other situations. But if you think that there could be another problem, and if I have enough material to make a presentation about that, just let me know. I think those 4 problems are general enough. I have some space-time estimates in the topic about turbulence, but they are not there, all of them. I have a paper written about that, but it's, you know that paper? It's in SIAM on numerical analysis with... Yes, but and the existence of the attractor in the case of the existence of an attractor for the subscales for the incompressible Navier-Stokes in the long term. Anyway, we can talk about that. But no, I don't have many space-time estimates. You mean general space-time estimates? Oh, general space-time estimates, not only for that.
Not only for that. Some highlights on that would be helpful.
Maybe I could do that right away, right now. Yes, maybe I should have done that, because it's an important, yes, it's important, yes, you're right. So, I just will give you just one estimate. So how do these estimates look like? This is important, because we know how the estimates in time look like, right? We know how the estimates in time look like. How do the space-time estimates look like? Well, the first point is that the solution U belongs, this is very important, to L infinity in time, L2 in space, intersection L2 in time, H1 in space. Okay, that's the first point. So estimates have to be given, if possible, in this norm. What is this norm? So this norm is the sup, or the essential sup, if you want, in time, the sup in time of the L2 norm in space plus the integral over time of the H1 norm in space, which essentially is the gradient of U squared. That's for Galerkin. For a stabilized method, we have something different. Okay? For a stabilized, something different. So what does it mean? That stability estimates, well, in fact, we use, that's what we use. We have the square of it, okay? The square of it, to make things consistent. So for the Galerkin method, stability usually is proved in this way. Stability is proved by saying that this is bounded in terms of the data. That would be for a solution that is, what does it mean? It means that the solution is continuous in time. I am integrating in time, okay? I'm integrating in time. The solution is the, and if you fully discretize the problem, the stability estimate is the following: max for all time steps of UH at time step n in the L2 norm, plus this is replaced by the sum from k equal 1 to the number of the total number of time steps of delta t times viscosity times gradient of UH at time step k squared. Is more or equal a constant that depends on the data. Okay, so those are the stability estimates. Okay, so the stability estimates that you will find, that you have to find for all methods, have to look like that: stability in this norm, and when you go to the discrete case, in this norm, the fully discrete in time. So this is continuous in t, continuous in time, discrete in x, in space, and that is fully discrete. Fully discrete. So your stability estimates have to look like that. What about your error estimates? Your error estimates have to be like that: max in time for all n of the difference between u at time tn minus uhn in the L2 norm in space, plus the space norm, which is sum for k equals 1 to the number of time steps of delta t times viscosity times gradient of u at time step n minus gradient of uhk squared. Okay, so that is how the error estimate has to look like. And how does that behave? It behaves as follows: if you are optimal, this is up to constants, the following: it is bounded by a term that depends of the power of delta t to the error in time. Let me call it order in time. How do I call the order in time? Let's call it p time, or no, let's call it k time, the order of the time approximation, plus h up to constants that make everything dimensionally consistent, k order in space. Okay, that's how the error estimates have to look like. If you are optimal, they have to look like that. Of course, that will be multiplied by what? What do you think that will be multiplied here? What type of thing will be here? Let's think about units. This is delta t to the power of the order in time. For example, if you use a first order scheme in time, this is 1. If you use a second order in time, that could be 2. Imagine you use a second order scheme in time. That should involve what? That, you see, has units of velocity. Oh, by the way, those are the squares, so this is 2. Just because I have the square here, okay? Just because I have the square. So that should involve what? That has to have units of velocity, and this is time to the power of whatever. So that will be what? What? It's only from the unit point of view you have a lot of information. So what should be there to make units consistent? What? No, length, no. This is not length. We are talking about time. Time approximations. What? That has to have, look, the product of this operator times delta t to the power of 2k has to have units of velocity, of u, or whatever, u. So, what should be there? Is there time unit? Are there time units on the left? No, there are not. I don't see time units there. What?
1 by time.
Exactly. And how do you get time dividing? How do you get time dividing? You should remember the error estimates that we wrote in time, in space, sorry. What were, you remember in a space, what?
That capital T.
No. Look, in a space, what did we say? That what was the interpolation estimate of the finite element method in L2? I said, it's in L2, the interpolation estimate is h to the polynomial order plus 1 with a constant, and here what?
Norm of
H?
H.
HP plus 1. And what's the norm u HP plus 1?
Gradient.
The semi-norm, in fact.
Pth norm.
Which what?
Norm of the Pth derivative.
P derivative. The key word is derivative here, okay? So this is the derivative of order P plus 1 in L2. Derivatives. Okay? So here what we have are the derivatives of u in time up to order kt of u, and that is squared. Okay? So that's what appears here. And the same for the time term. For the time term, you have the semi-norm of the unknowns in kx plus 1. Because on the left, yeah, okay. And then there are constants. Here there is the viscosity, because the viscosity appears here, because the only way to be consistent with these units is to have the viscosity here as well. Okay? So this is consistent with this is consistent with this, and of course, both are consistent one with the other, because we want to add them up. So that's the way estimates look like. When you have pressure, the problem is that pressure, Navier-Stokes, pressure and Navier-Stokes are something that don't match very well. Usually pressure estimates are very difficult to obtain, because once you have velocity estimates, you can obtain pressure estimates afterwards. You can obtain pressure estimates, and the pressure estimates usually look like as follows. Look like maximum in T for n of pressure at Tn minus P Hn bounded by something that depends the velocity error. Velocity error. Okay. But those are difficult to obtain. Not only that, well, this may be too much information. Not only that, but it turns out that if in time you have an error of order kt for the velocity, remember that this 2 is because I'm considering the square everywhere, okay? So you could take the square root everywhere, and that would be it. Now, in fact, by the way, it's better not to put the square and put the square root here. Oh, no, sorry, no, that is okay. That was okay. No, that was okay. So the problem that we have with the pressure is that if velocities are of order kt, pressures are of order kt over 2. That's a bad thing. Depending on the method, are kt over 2 or kt minus 1/2. You either lose 1/2 or you directly divide by 2. So for example, for Navier-Stokes, if you use a second order scheme in time, the solution is going to be second order for velocities, but only guaranteed, in practice you get more, but only guaranteed first order in pressure. Only guaranteed, okay, first order in pressure. That's a famous paper. In the case of Galerkin, that's a famous paper by Haywood, series of paper by Haywood and Ranacher in the 80s, okay. They first proved the error estimates in time. So what happens when you use a stabilized method? When you use a stabilized method, you get something similar.
On the stability estimate, constant stability estimate, usually that is very large.
Oh yes, the constant may be very large. For example, you mean in terms of what? Because if you're talking about in terms of viscosity or in terms of what?
Whatever the constants involved, I think usually it comes in terms of T also. It comes.
Oh yes, no, but that's for Navier-Stokes. That is, you're right. So the problem with Navier-Stokes, this is an additional remark. The problem with Navier-Stokes is that when you try to control the nonlinear terms that have to be controlled, that constant happens to behave as e, the exponential of the time t until where you want to compute, and not only that, very often multiplied by the Reynolds number. So it's terrible. So those estimates are very bad. in time, okay? That's also an important remark. Yes, I didn't have material about that because this is more analysis rather than stabilized methods and general Navier-Stokes, okay? But yes, this is very important. Those estimates, one says that those estimates explode in time. So far we do not have any good estimate that remains bounded for all time, okay? What happens when you have stabilized methods? What is the problem with these estimates? The problem is that when viscosity is very small, we have very small information. By the way, you see that we always have information in L2. The information in L2 is never lost. So that's something that has to be taken into account. In a time-dependent problem, we always have the estimates in L2. I mean, in spite of the fact that the constant may be large, but we have estimates in L2. What is misleading, what is or not meaningful, are the estimates in a space. Why? Because if the viscosity is very small, that's going to be very small. So we're going to have nothing. Okay? So what happens in the case of a stabilized method? What do you hope for? What do you hope? When you are analyzing a stabilized finite element method, what is the hope? The hope is that you will be able to replace these by what? To replace these by what? That is the objective. Who tells me? By the triple norm. So the target, the objective of the analysis of stabilized finite element methods in time, for the Navier-Stokes equations, is to replace that norm that is meaningless, new gradient, or meaningless, not meaningless, but has very little information. For example, for Navier-Stokes, it is convenient to replace it by new gradient of UH plus tau UH gradient of UH. And that gives us control on the streamline derivative. You know? So the objective of a stabilized finite element methods, when you do the analysis, is to prove this. Okay? To prove that you have similar estimates, but with the triple norm that gives you more information. So it gives you information not only on the gradient multiplied, so the gradient is much more than the convective derivative, but this is multiplied by the viscosity, which may go to 0. And that when the viscosity goes to 0, that still remains something. The technicalities are very deep in the case of Navier-Stokes, okay? In the case of Navier-Stokes, there are many technicalities involved, okay? Many details involved. No, in fact, the truth is that I didn't plan to talk about that analysis. I think this is really advanced, so that would require a lot of preliminaries. But you are right, giving the general overview maybe is important. Okay. Anything else? Okay, so tomorrow we will finish this chapter with a short section on fractional step methods, and then we will move to turbulence.